So let's start off with the topic for today. Today we will be starting off with LOSJ. LOSJ and LOSJ is related to dummy variables. Is related to dummy variables. Okay. Now, uh, the concept of dummy variable is first. Let me read the statement out. Formulate and interpret a multiple regression including qualitative independent variables. Okay, qualitative independent variables means dummy variables. Now what this concept is trying to explain over here is that in real life we have learned in multiple regression that there will be multiple independent variables. That's fine. We have also learned in the multiple regression that we need to test for each and every variable using either a t-test or the entire equation using a f-test, etc. That is also fine. But and the third thing that we have learned is that multiple regression, the independent variables coefficient can take a range of values. So suppose if it is GDP, it can take values in trillions. If it is a crude oil price, it can take the respective value, and etc, etc. So depending on what you forecast, the value of the value of the independent variable, accordingly those values can vary. Okay. However, there is a concept in the world of independent variables where, or there are situations in real life where you see that it's kind of a on or off thing. It's kind of a yes or no thing. It's kind of a whether that thing is yes, binary thing. Binary situations that we come in, or binary independent variables which are binary in nature. So if everything, the entire equation is correct, if world war is not happening, if world war happens, then the equation will change, kind of a thing. These type of items are called binary in nature. For example, we all are aware of the Russia Ukraine crisis that happened recently. Okay, I think I took this kind of a reference also in the last class, that if suppose I am predicting a share price, suppose I'm taking a simple linear regression, suppose share price of Cardinal Health is equal to $13 plus, say for example 0.75 into it's health industry. So uh, let's link it to GDP. Let's not think, or S&P 500. So S&P 500 return for last 1 year return. Let's assume it's a hypothetical equation. I have not applied any maths or logic on that. I'm just trying to take an example. Okay, this equation holds good in normal scenario. In normal scenario, however, if suppose world war happens, if suppose, God forbid, but if suppose world war happens, then do you think that the entire stock market can stay as is, or there will be a severe massive decline that the stock market will experience?
Decline.
It will be a massive decline. It may happen that the asset prices may reduce by more than 50% or more than 70%. That kind of a situation may also arise. Okay, so this, all these things happen in normal scenario, but there is a, and for World War 3 there are only two responses possible. Either it will happen or it will not happen. So either a yes or a no, you have to be definite in your answer, or the situation has to be very definite. It cannot take a range of values that okay, world war 0.2 degree has happened, or 0.3 degree has happened, or 0.5 degree. That cannot be an answer. Here the value of the coefficient, instead of 0.75, it can also be 0.60, 0.50, or 0.20, or even 1.50. There can be a range of values for the coefficient possible. There can be a range of values for S&P 500 also possible. This is possible. But here in such kind of scenarios, whether COVID is eradicated or not, whether the world is suffering from a pandemic or not, there can only be two responses, yes or no. You cannot have a midway around this thing. So whenever such kind and these qualitative factors affect, for example, let me take a company specific example now. Cardinal Health. These all health companies, if you go through their annual report, their biggest asset is patent, because all these companies, they invest a lot of money in their research and development to find new medicines or new kind of cures for various kind of diseases. If you go through the balance sheet or annual report of Cardinal Health, you will see that they have wrought 1300, 1600, 2000 patents, and their patents analysis will help you estimate the future expected revenue. This is the business. Suppose everyone was working for COVID. Suppose Cardinal Health is also working on finding a COVID cure, a perfect COVID cure. Okay, in that situation, if suppose Cardinal Health is able to find that thing and Cardinal Health applied for a patent, so the outcome of that application of patent can either be a yes or a no, and this is a dummy variable, because if Cardinal Health gets that patent, then its share price may increase by 50% or 60% or 100%. If it doesn't get that patent, then its share price may decline by 20 or 30%. So this kind of this getting a patent from a court, from a US court or from wherever, that particular thing only the only responses can be a yes or a no. Whenever there are, so this statistic says that there are situations where, when you are trying to determine the value or create an equation for a dependent variable, in that situation, among other factors, there are qualitative factors also. Qualitative factors means you cannot value them in numbers. It's not possible. I cannot assign a number for a patent, 0.8 degree patent. No, it's either a patent, a yes or a no. We call it as dummy variable, and the value of the coefficient of a dummy variable can either be a 1 or a 0, not a midway. So either it happens or it doesn't happen. That's it. If it doesn't happen, then you can include the dummy variable. Okay. If it doesn't happen, when you will assign the coefficient value as 0, automatically that goes out of the equation, or that effect is nullified. Okay. But when you also know and recognize that when that thing will happen, it will have a significant impact on the dependent variable, and that is why I will have to involve this particular thing as well to make my model or to make my equation more accurate or more representative of a real life situation. This is what is called dummy variable. Okay, so the conclusion is very simple, that you will be assigned the equation, although we'll work around that equation kind of a thing, that how dummy variable, when they take a value of 1, then how it is treated, all those things will come to. But the structure is very simple, that you will be provided with an equation. In that equation, you will be told that these are the qualitative factors or dummy variables in exam question, and you have to, by reading the item set or the vignette, you have to conclude whether that dummy variable slope is taking a value of 1 or 0. If it takes the value of 1, then only it has a meaning. If it takes the value of 0 or that situation is not happening, then the dummy variable is not going to have any impact on the dependent variable. Okay, that is something which is there. And yeah, this is the situation. And okay, there is one very lengthy example which they have taken with regard in your CFAI curriculum with regards to dummy variable. It's a very famous model. So let me give an extract to you, or an idea to you about that particular thing. It's the model of Mazumdar and Sen Gupta, which was developed in 2005. I'm just trying to give an overview to that particular thing, which provide a complex example of an investment application of multiple regression using dummy variable. Okay, what they are trying to determine is that Mazumdar and Sen Gupta tried to determine, one second, yeah, they tried to determine the loan spreads relative to LIBOR. Loan spreads relative to LIBOR. Okay, here our focus should not be on the complexity of the model, because we may not be that pro enough to understand this kind of a complex model. Here my understanding over here is, or my purpose to show this particular thing over here is that how in real life, when we all will be building our models, you also will be building models going forward. In that situation, how you can make use of dummy variables in your particular situations. Okay, so the concept is the we are trying to value the loan spreads relative to LIBOR, loan spreads relative to LIBOR on a private debt contract. Okay, and they say that these is negatively associated with the quality of the financial statement disclosure. So suppose loan spreads, okay, related to LIBOR, loan spreads related to LIBOR, this is my dependent variable, which is getting explained by suppose there must be a B0, which is your intercept, plus they are saying so dependent variable, which is the spread, is quoted in basis points over the labor. The independent variable includes the average total disclosure. So disclosure B1 into disclosure. Disclosure means financial disclosure. Disclosure over here means financial disclosure. As the quality, okay, apply common sense. We are trying to measure spread over LIBOR. Okay, if suppose there is a company, if suppose there is a company which is giving very high level of financial disclosures, then will your reliability will be more on that company, or there is another company which is giving very less low level of financial disclosure, will who on which company you will rely more?
The first one
The
that is
first
giving
one,
more.
that is giving very high level of financial disclosure. If that be the situation, if that be the situation, then my next question is, if you rely more on someone, then will you charge higher interest or lower interest compared to if you rely less on someone?
Lower interest.
Lower rate of interest you will charge. So B1 discount, that means what is happening is that if the disclosure quality uh, is not up to the mark, in that situation only our this what you say, so disclosure score is there. If this is not up to the mark, our spread will increase. If this is up to the mark, our spread will decrease. Okay, the next situation that is there is the SD of the daily stock return. So SD STD, what they have measured it as STD RETN, daily stock return. Okay, this is the second variable, and the third variable is the current ratio. Or sorry, the third variable is the current ratio CRATIO, plus the fourth variable is the market to book ratio MKBK. Okay, all these four that you are seeing, P1, this discount. Suppose I assign B3, I assign B4. This discount, this HD of daily return, this current ratio, this MK, market value to book value, all these are true independent variables. All these are true independent variables. Why? Because their slope can take any value and they will always be there. They are not binary in nature, they will always be there. Okay, so these are the true independent values, the normal independent variables which we have learned till now. And this equation doesn't stop over here, but Mazumdar and Sen Gupta, which are assumed to be financial wizards in the financial industry, they add three more variables over here. Okay, and those three variables are dummy variables. The first is secure, whether the loan is secured or unsecured. If the loan is secured, then the value is going to be, the spread is going to be lower. If the loan is unsecured, the spread is going to be higher. Okay, so here in security, again you can only make two responses, yes or no, whether the loan is secured, whether the loan is unsecured. There is no midway possible over here. Okay, the second situation, the second dummy variable is the bid. What is bid? One second. Bid, which is one if the loan contained the option to price the loan relative to a different index. So the pricing of the loans, if you go in real life, the pricing of the loan happens generally relative to Moody's and S&P. So if the company is listed, then their Moody's and S&P ratings are also pegged. These spreads are pegged to the S&P and Moody's rating. So this bid, you can think of it as kind of a pegging, that if the Moody's and S&P rating decreases for any company, automatically its loan cost will also increase and its spread will be higher, and vice versa. So again, whether that bid has declined or has not declined, the rating has changed or has not changed, again there can only be two responses. It can be yes or it can be no. There cannot be any midway to this thing. And the third situation is, or the third thing is, restructuring, whether the loan is taken for any corporate restructuring or not. Restructuring, these are standard terms that they have used, so we have to use it as is. I'm using it as is, which they have used in their real model. Okay, so this is restructuring, whether the loan is taken for any corporate restructuring or it is not taken for any corporate restructuring. So these three are dummy variables, while the above four are true variables. There is no such term in statistics called true variables, but I am using it for here for the convenience of explanation in class. Okay, and these are dummy variables. Okay, so normally an equation will always be impacted by these four items or these four independent variables, while all these can take a value of either 1 or 0. If they take the value of 0, then they don't come into play. If they take the value of 1, then individually each and every will come into play and will change the value of the spread that is there in the loan portfolio or the loan spread. Okay, this is the impact of dummy variable.
So it's just extending the equation.
Yeah, extending the equation, but yes, there is a meaning to that also, because when you will also create a what you say, uh, that equation in real life, as I was saying, you will also be faced with the qualitative factors. For example, as I told in simple terms, if I have to say, for example, cardinal health and patent. So if there is a big patent for which they have applied, the outcome can only be a yes or a no. Suppose Facebook, you are trying to forecast or create a model for Facebook, you linked it to ARPU, etc., etc. But suppose there is another platform, YouTube advertisement, suppose, and YouTube has started its advertisement, and YouTube is planning to reduce the advertisement cost, which is going to significantly impact the Facebook ARPU, average revenue per user. Now that decision is pending from YouTube. You can think that decision outcome can be either a yes or a no. So in that situation, if that kind of a scenario you are in and you are a Facebook analyst, you will try to add this dummy variable, because this dummy variable is going to create a significant impact on the Facebook's ARPU as well as the share price. If you go into the recent call, like the latest call transcripts of this particular company Facebook, then they have also mentioned that their ARPU has declined. One of the major reason is that YouTube advertisement shift of consumer or advertisers to a different platform, because the more economical platforms and more specific platforms are now becoming available compared to Facebook. So this kind of real life scenarios or real life example I'm trying to give you to make you understand that how a dummy variable is applied in real life. Okay, moving on to the next thing. Now I hope you got a fair idea about what dummy variable is. Now moving on to the concept part. Okay, now what does the slope value or what does the value of the dummy variable represent? Okay, so they say the value of the dummy variable or the estimated regression coefficient for dummy variable indicates the difference in the dependent variable for the category, indicates the difference in the dependent variable for that cat. So before that you have to understand, if suppose there are you are trying to create an equation from dummy variables, and there are n classes of dummy variables, then the number of independent variables you will add, or number of dummy variables you will add, is n minus 1. For example, and the example is also discussed in our textbook, suppose I am trying to predict EPS for every quarter, EPS of a company for every quarter. How many quarters are there in a year?
Or
4 quarters, correct? These n classes here represents 4 quarters, because I am trying to predict or calculate the impact total EPS using all the 4 quarters, and all these 4 quarters represent the n classes, quarter 1, 2, 3, 4. Okay, if I have to account for such situation, the equation that I will create is of 3 quarters only, with fourth quarter being a reference point that will form part of my slope, that will form part of my intercept coefficient, there is a reason to this, we will come to that. But if I am to write that equation, or the equation that we'll be using for this particular thing, EPST, that is the earnings per share that we are trying to forecast, is B0 plus B1 into Q1 plus B2 into Q2 plus B3 into Q3. There is no B4 into Q4. Now the statistical reason for this is that if I add a B4 into Q4, in that situation my entire multiple regression model will become a failure. The reason is that there are some basic assumptions for creating any regression model. We have not yet covered those assumptions, because those assumptions are in LOSF, which is, as per our textbook, if you go into that flow, it is scheduled after this particular topic. But there are 6 odd assumptions that we will understand, which will lay our foundation for understanding why heteroskedasticity happens, why serial correlation is a problem, why multicollinearity is a problem, why model misspecification is also a problem, which is the next part of our particular reading. However, all these are problems, the terms, the big terms that you may, if you have hovered through the pages, the big terms that you have seen, heteroskedasticity, multicollinearity, and all these things, these are not solutions, these are the problems with the regression model. So all these problem arises because of the violation of the assumptions. Statistics and regression is very strict with the assumptions that it proposes. If the assumptions are getting violated, the conclusions from the model cannot be reliable. It is very straightforward thing that regression is trying to say. Hence, whenever you are creating any model, you have to ensure that all these 6, whatever the assumptions are, those assumptions are adhered to. Okay, otherwise the whatever conclusions you are drawing, the conclusions will not be fruitful, or it will not be reliable. Okay, or in all those assumptions, one assumption is that there should be no exact linear relationship between independent variables. There should be no exact linear relationship between independent variables. So Q1 and Q2 and Q3, these should be unrelated. If I am taking a model over here, discount and standard deviation of return, these current ratio and the market value, book value, all these 4 items has to be uncorrelated between each other. There should not be any linear relation. Non-linear relation is possible. Non-linear relation is possible. Understand the fact, linear relationship is not possible over here. In exam, a question will come. In exam, they give question that the assumption of the regression model says that there should be no relationship between two independent variable. Incorrect. The regression assumption says there should be no linear relationship between independent variable. Non-linear relationship is possible. Okay, and these questions come in exam. Whatever I am saying, these are actual exam questions, whatever just I told you. Okay, so the point over here is that these 2 items, or these all the independent variables, should be uncorrelated That is one of the assumption. Now if I take the fourth quarter as well, and if here we are taking the actual quarterly EPS, which we are not taking now, if we take actual quarterly EPS, in that situation it is very much logical to understand that EPS quarter one result is going to impact EPS quarter fourth result, or third result, or second result. That means it will be correlated with each other. Hence we are, whenever you will be in a situation of that there are n classes, n classification possible, you will take n minus 1 dummy variables only, not the all the dummy variables. With one dummy variable will become your reference point. So here the equation is structured in the manner that b0 represents the fourth quarter EPS, while b1 represents what, you know, the difference between the fourth quarter EPS and the first quarter EPS. First quarter EPS. Similarly, B2 represents the difference between the fourth quarter EPS minus the second quarter EPS. B3 becomes the difference between the fourth quarter EPS and the third quarter EPS. These are not actual EPS values, these are the differences. And all these are dummy variables. You have to check whether we are in quarter 1, quarter 2, or quarter 3, or quarter 4. If we are in quarter 1, the value of this dummy variable, that is B1, will be 1 and all other will be 0. So the equation will become B0 plus B1 Q1. If we are in quarter 2, then this will excuse me. If we are in quarter 2, then this will become 0 and this will become 1, this will become 0. The equation turns out to be B0 plus B2 into Q2. And similarly with the third quarter. And if you are in fourth quarter, then all these three terms become 0 and only B0 remains, which is my fourth quarter EPS. Are you getting an overview of what I'm trying to explain?
Is this because the dummy variables represent quarters in a year? But if the dummy variables represent like different things, it doesn't necessarily mean that only one dummy variable can have a value. The other ones have to be 0 or no?
It can be that multiple dummy variables can have value. That is what you are trying to say.
Okay,
right?
yes. Okay.
Yeah,
yes.
It is possible. It is possible. Here in our scenario, we can only be in one quarter at any point of time in a year. That is why other quarters value is 0. But if that kind of a situation happens, suppose there are 2 patents. Suppose, let me go back to my simple example of Cardinal Health, share price Cardinal Health, and there are 2 patents. One patent is for COVID, the other patent is for cancer. Suppose, okay. So, and both the patents are going to have a significant impact on the share price. It can be possible that for both the patent, my value turns out to be 1, or for one patent, the value is 1, one patent, the value is 0.
But in this scenario, do you have an intercept?
Yeah, we have an intercept. I just took this example. You can take a hypothetical intercept of 13 and S&P 500 relation also.
Okay, so that said, you did not include the fourth quarter dummy variable because the intercept stands in for the fourth quarter.
Yes, that is what this model is saying, that you have to take n minus 1 dummy variables if you have n classes. That is 1 less. Because if you take all, then it will result in a problem of linear relationship between dummy variables. So what happens is, one dummy variable is becoming my reference point, which is the fourth quarter, and here I am taking only the differences, not the actual values of dummy variable, actual values of EPS. Think logically. Any quarter EPS, suppose quarter 1, quarter 2, quarter 3, they will be linked to each other, or with quarter 4, correct? But if I am taking the differences, first that linkage part is gone, and my reference point over here becomes the fourth quarter EPS. So one dummy variable among the n classes, one class or one value has to become the reference point, and all other classes will be quoted in that terms only, so that the linear relationship is gone between the independent variables. Yeah. Okay, we'll come to this example again with solving numerical values, but just 1 second.
Hey, Mohit.
Yeah, hi
This
Nina.
is Hi. Thank you. I came in a little bit later, so if you don't mind, just for my notes, can you tell me what is the purpose around the dummy variable, please?
Okay, the purpose is very simple, Nina, that dummy variables are qualitative variables. So suppose you are in a situation that, so normally what we have discussed, the independent variables, those independent variables are that you can take a value of 0.75, they can have a value of 0.6, 0.5, 0.2, 1.5. That means they can have a range of mathematical value. Okay, however, there are certain situations which are called qualitative situations or qualitative variables. In that situation, what happens is that either a yes or a no is only possible. For example, suppose there is an example of Cardinal Health, and these health companies are in patent business. The most important thing, if you go for any pharmaceutical company, their annual report, the most important thing for them is their patents. Okay, so if suppose they have applied for any patent, suppose they have applied for a COVID vaccine patent, okay, which is going to be a very important driver for them. In that situation, the only two outcome possible for this COVID vaccine patent is a yes or a no. Correct? There is no third outcome possible. Okay, these are called qualitative factors or qualitative variables. They can, if the answer is no, any which ways they go out of picture, so the value that they will attain, their coefficient will attain, is 0. But if their answer is yes, they have the ability to affect the dependent variable significantly. And so you cannot leave that thing out of the model, you want to include that thing in the model, but you also know that it may so happen for majority of the time it may not affect, but for some time it will happen affect, and the effect will be very significant. So you have to include that, but in that nature only, that the key is off and key turns on only when the situation is on, basically. So it will be yes, or when it is yes, it will take the value of 1. Another example you can think of is the Russia Ukraine crisis example that we discussed over here. So all the companies in the world, all the share prices normally may increase, decrease, but if there is a world war situation that may arise in any case, in that situation we all know that the share price of, be it very, even if very strong, fundamentally very strong company, then also the share price will decline significantly. Okay, so that world war is a dummy variable. It will be 0 for majority of the time, but when it will be 1, like when the situation will be there, in that situation it will have a overriding impact on all the share prices of the company, or that is there. So it can be a yes or a no, and for world war it can be a yes or a no. Either we are in world war or we are not in world war. There cannot be a midway possible. There cannot be a zero point 0.7 world war or a zero point 0.6 world war or a zero point 0.2 world war. It is a world war or it is not a world war. It is a patent, I got the patent, I not got the patent, and kind of a thing. So these are called dummy variables, and here, using dummy variables, we try to account for these particular thing in our model or in our equation. This is the background which of dummy variables.
Okay, thank you so much. So it's when basically when there's pretty much an absolute situation where it can be only one or two things, yes or no,
Yes
right
or
or
no?
wrong, left or
Yeah,
right.
right or wrong, right or wrong.
And we typically ignore this, but only the times that we do consider this is when it can impact the entire equation or picture overall.
Right, exactly, exactly.
Okay, thank you.
Okay, now dealing with the equation. like mathematical dealing. We got the background of what dummy variable is, how to create it in form of an equation. Now suppose the dummy variable value is 1. Suppose now how you will deal with that thing in the equation. So they say there can be two situations possible in this scenario. One second. Dealing with dummy variables. They say there can be two situations possible. Number one is called slope dummy. Slope dummies. And number two is called intercept dummies. Okay. So suppose our simple equation is y is equal to b0 plus d0 into d. Suppose the true independent variable, and plus, sorry, this d0 represents the dummy variable. So when in exam, from standard notation point of view, I'm saying when in exam you are getting an equation where they have used, so the standard notation for a true independent variable is b1 into x, which we have been using since the start of the class. But if you get d0 kind of a thing or d0 kind of a notation, you can safely assume that this is dummy variable. Okay. So over here, what is happening is, one second. Yeah. Okay, over here they say that there are two ways of dealing with dummies. Number one is you adjust, or dummies are getting adjusted with the independent variable itself, with the slope of the independent variable. So suppose if this situation you look at, if I am closely observing, suppose the value of the dummy is 1. Suppose in that situation what happens is b0 plus, the equation can be structured as d0 plus b1 into x plus ei. Now whenever the value of the dummy is 1, like the dummy situation is there, you have to put the required value and it will be adjusted, it, or it will change the value of the coefficient itself. It will change the value of the coefficient of the independent variable. This, since this is changing the value of the coefficient or slope of the independent variable, these are called slope dummies. Okay. The another situation is y is equal to b0 plus d0 into d plus b1 into x plus ei. Now in this situation, if suppose d0 turns out to be a value, in that situation what will happen is that b0 plus d0, it will be adjusted accordingly. So when it will have a value, the dummy will have a value, and b1 into x will be a separate number, will be a separate thing. So here it is adjusting itself to what? Adjusting itself with the intercept term. So there again, I'm repeating, there are two situations in which is possible. One is that the dummy adjusts itself with the slope, and it will result in change in slope of the independent variable, and that is why it is called slope dummy. The second thing is that it is not adjusting itself with the independent variable or any of the independent variables. In that situation, it will automatically be a standalone number, and intercept is also a standalone number. So two standalone numbers cannot stay, obviously they will be added or subtracted among between with each other. So automatically this term is adjusted, or this dummy is adjusted with the intercept, while the slope of the independent variables remain as is. In this situation it is called the intercept dummy. Okay, there is another situation where both kind of dummies can exist in one equation only. So one will be a slope dummy, one will be a intercept dummy. So that is called a combination of dummies. So that is also possible. Is this okay?
Should we memorize these formulas? Because like the first slope dummy, it the equation mathematically makes sense when you factor out the x. However, for the intercept dummy, I don't see how mathematically
So
you can.
mathematically, Dennis, what it will be? It will be a value. So D0, the value of D0 will be 1 or suppose any other coefficient value, and D will also have a value. Correct. So the only thing that will remain is a numerical number without any variable factor. Intercept we always know is a numerical number, and this, after putting the values, this will also be a numerical number. So automatically these two numerical numbers will adjust with each other, and that is why we are saying it is B0 plus D0 or intercept dummies. You can think
So
of it,
that.
you can think of
Mhm.
it in that way, that if there is a dummy variable which is not a slope dummy, automatically it has to be an intercept dummy.
Okay. So in the intercept dummy, the D is 1. That's what you're saying.
Yes, the
Okay.
D0, D is 1, and D0 can be any value depending on the whatever the value, whatever the situation is, the value that comes, that will be the value. And D
Okay.
is
So
1.
so then you don't need to necessarily put the B0 plus D0 in parentheses. You can just add them because they're
You
numerical.
you will automatically add them when I will supply you with the value. Suppose
Okay.
I
Yeah.
supply you with the value, then automatically you will add them. So I am showing it over here. That may make things confusing, but actually this is not a difficult thing. This is like that, if suppose I give you a value of B0 as 0.13, suppose I give you a value of, there is a dummy variable, I say that dummy is true, so that means it is 1, and the value is 0.15 plus b1 into x. What you will do, you will make this equation more simpler as 0.28 plus b1 into x. And when you do that, which is a by default, anyone will do that, automatically this become an intercept dummy.
Okay.
Okay, so now taking our original equation, I'm just trying to explain that equation a bit. This particular equation that we have in, if suppose we take a numerical value for these equations, just 1 second. If we take a numerical value for this equation, the standard equation, okay, supposedly if our equation over here is, let's take an example one. Okay, so EPS is equal to B0 plus B1 into X, uh, B1 into Q1, sorry, plus B2 into Q2 plus B3 into Q3. Okay, where these are the 3 quarters, and B1, B2 represents the differences. Now suppose if I supply you with the value, the last 10 years average value, last 10 years average fourth quarter EPS, average fourth quarter EPS is 1.25, and the equation is structured below. EPS T is equal to 1.25 plus, say for example, 0.75 Q1 plus, or sorry, minus 0.20 Q2 minus 0.20 Q2 plus 0.10 Q3. Okay, if this be the equation, automatically you get the values of last 10 years for the first quarter, second quarter, and third quarter also. If I am to ask you what is the average last 10 years average value for the first quarter, what will be your response? Well, I have already defined that B1 represents the difference between the fourth quarter and the first quarter EPS. And I ask you, based on this information, what is the first quarter average EPS for the last 10 years?
Isn't it just 1.25 plus 0.75
Yes,
Q1?
automatically because this represents the difference. The B1 over here represents the difference between fourth quarter and first quarter EPS, and over here the fourth quarter actual EPS value is given, and here the difference value is given. So last 10 years average value is automatically 2. So for Q1 average, let me take new page. Average first quarter EPS is equal to 1.25 plus 0.75, that is 2. Similarly, average second quarter EPS 1.25 minus 0.2, which is 1.05, and the average third quarter EPS is 1.25 plus 0.10, that is 1.35. Since all these are dummy variables, as I told, because at any point of time you can only be at one of the quarters, you cannot be at all the quarters at any point of time. So if you are at fourth quarter, all these dummies are 0, the average value is 1.25. If you are in the first quarter, the average EPS expected value is 2, so is for second and third quarter as 1.05 and 1.35 respectively. Okay, so this equation, this is a simple regression model which helps you understand that how dummy variables work and interact with each other. Now if suppose you want to test for any of the particular variables, automatically it will be easy for you. If suppose you want to test for B1, then you will assume that B1 is equal to 0. Whether if B1 is equal to 0, if B1 is equal to 0 over here, in that situation you can assume, or you are assuming, that the fourth quarter EPS and the first quarter EPS are equal. Because if B1 is equal to 0, suppose we are in first quarter, so automatically the two dummy variables are 0. Now you have the equation reduced to as B0 plus B1 into Q1. Now, if the first quarter EPS, the B1 value turns out to be 0, what it will mean is that the first quarter EPS and the fourth quarter EPS are equal. This will be automatically, this will become the test for this situation. Since B0 is the fourth quarter EPS, B1 is the first quarter EPS. Suppose you are in quarter 1. So B2 and B3 are 0. They go out of picture. They are dummies and they take a value of 0. Now you have only two things, B0 plus B1 into Q1. Okay. Now if I am testing, I am doing a hypothesis testing of, say for example, that the value of B1, slope testing, whether slope is statistically significant or not. So automatically my test t test would involve B1 is equal to 0, alternate will involve B1 does not equal to 0, and so on and so forth. So you can do a t test and you can conclude whether this particular thing is statistically significant or it is statistically insignificant. Okay. Let's perform one test over here. Example 1. Suppose the standard error of the coefficient B1, okay, is equal to 0.15 from the EPS regression model. Test whether first quarter EPS is equal to the fourth quarter EPS at 5% alpha. Test. What will be your conclusion? HA will be what? When you test for statistical significance, what is the HA? The HA is that B1, because we want to prove that it is not it is statistically significant. B1 does not equal to 0. Then automatically H0 will be that B1 is equal to 0. Now how will you do a t-test?
You just take the 0.75 minus 0
Right.
over the standard error
Of
coefficient,
0.15.
which is 0.15.
Right. So the t-stat value will be 0.75 minus 0 by 0.15, which is equal to 5, correct? And the t-stat is there. What is the other one? T-critical. T-critical value you can check from the table, 5% alpha. And yes, it was mentioned that last 10 years averages are being taken. Last 10 years averages are being taken. So n is equal to 40, because for every last 10 years 4 quarters data is getting taken. So 4 quarter into 10, 40 data is taken. And k is equal to how much? K is equal to 3, because there are 3 variables that we are taking. So k is equal to 3. Hence n minus k minus 1 will be equal to 36. So in t table at 5%, two tail, because equal to sign is there, at 5% two tail, you have to check for that thing. What is the t critical value you are getting?
It's around 2.03 because it's a little bit under the 2.04
Yeah.
in the table.
Okay. Just 1 second. Let me find it also. Are others are also getting this particular thing?
Yes.
Yeah. So at T table, two tail, 5%, and since we have 40 and 30 only, so 2.02, 2.04, somewhere around 2.03 something, which we can conclude. It was 2.021 and 2.042. So between that, let's take a rough average number of 2.03. So automatically we reject null, because the range was between 2.03 to minus 2.03 and our value is 5. So we reject null and conclude that the first quarter EPS and fourth quarter EPS are statistically different. Conclusion, we reject null. Conclude that first quarter and fourth quarter EPS are statistically different. Okay. Okay. This ends our dummy variable concept. Any question on this part? Anything you didn't got?
I just, in the question, it says test whether the first quarter EPS is equal to the fourth quarter EPS. When we see that, do we automatically assume that we are trying to see if there's significant different from zero?
One second, sorry.
Okay.
What is the question?
So the question is asking whether first quarter EPS is equal to fourth quarter EPS.
Right.
When we see that, when we're comparing two things, is what we're trying to do, is it trying to prove that they are not zero?
Yes, because automatically that you are trying to prove that. See, they will be equal. They will be equal when B1 is equal to 0. If over here B1 is equal to 0, so suppose, as I told, suppose we are in first quarter.
Okay.
So B2 is 0, B3 is 0. So those are gone. Now the equation is B0 plus B1 into Q1. That is the only equation. If, and we are over here estimating EPS T. EPS T means EPS 1, 2 or 3 or 4. Okay, so now over here what we are trying to estimate EPS 1, and here if B1 is equal to 0, then EPS 1 will be equal to B0, and B0 is EPS 4. So automatically the maths, ultimate maths becomes that first quarter EPS is equal to fourth quarter EPS. Did you got this point?
Yes, it's clear now.
Yeah, that is why they are using that particular term. Okay, I assume there is no other question on this part, right? So let's proceed ahead. Now we are entering into, you can think of it in that way, kind of a second set. We are kind of moving into the second set of the discussion, or second set of the reading, which deals with, or which will deal with assumption, violation of the assumptions. Okay, so all the concepts of heteroskedasticity, serial correlation, and this multicollinearity, etc., all these will come into play. Now what I will do over here is that, to sum this particular part, I will, once again, okay, so let's, so here there are 4 things that you need to answer. Okay, just one second, just one second. Yep. Can you see this Excel screen?
Yes.
Okay, so one second. Okay. Now there are, in this particular scenario, we will be dealing with, as I told, first we will be dealing with the assumption. So I will explain you. But before that, you have to understand that whenever there will be any violation that we will deal with, which are heteroskedasticity, multicollinearity, and serial correlation. These three things we'll deal with. In that situation, you are responsible in exam for four things to know. Okay. The first thing is, what is the violation? The first question is, what is the violation? The next question is, what is its impact on regression? So whether the it results in uh, regression tests to be reliable, not reliable, so whether we can rely on that or not, etc. The third is how to detect the violation, and the fourth is how to correct the violation. Okay, all these things are mentioned in your textbook, but what we will do is that I will try to create a summary over here so that you don't need to go through pages when we are done. Once you have to read everything that I say that first time when you are doing, you should do with your book, because there will be a lot of detailed explanation, etc. But after that, you can refer to this summary. This will make things bit easier. Okay, so we'll maintain a summary of these particular points over here. Yeah, so the first thing that is there is Heteroskedasticity. Okay, so this is the first item that we have to understand. Yeah. Okay. Okay, now before that, first understand what the assumptions are and what is the important of the assumption. Why the assumptions are so called. First thing, our test statistic, our test statistic for t test was uh, estimated regression coefficient, estimated coefficient, let's put it simple, minus hypothesized value divided by standard error. Okay, the standard error of the coefficient, the standard error of the coefficient is measured using the standard error of the estimate, SEE. and standard error of estimate is nothing but the SD of error terms. SD of error terms. Understand what I am trying to say? I am trying to say that if any of the assumptions are violated, if any of our assumptions of regression that we will be discussing is violated, this assumption of HD of the error terms or SCE will be incorrect. If this SCE will be incorrect, then the standard error of the coefficient will also be incorrect. Our slope will or coefficient value will not be impacted. Do remember that. Even if my regression assumption or regression assumptions are violated, then also my slope coefficient is not going to be impacted. What is going to be impacted is my standard error. If suppose my standard error is too low, think if my standard error is too low, what will happen? What will happen if my standard error is too low? My t stat value will be
Hi.
high. If my t stat value will be high, then what will happen? Will we majority of the times reject null or fail to reject null?
Reject, but it may be wrong.
Exactly. We may reject the null when it may be wrong. We may say that this independent variable is statistically significant even when it is not statistically significant. So this makes my regression model unreliable. This is the impact. Opposite you can understand. So if SE is too high, then even if a right independent variable may be we may fail to reject null for majority of the time. So this is the problem with the violation of the assumptions, that this assumption will affect the standard error of all the coefficients, and standard error of the coefficients will automatically impact your t-test, your f-tests also. Okay. Now, what are the assumptions? LOSF. Explain the assumptions of a multiple regression model. There are 6 assumptions, majority of which are related to error term. As I told, majority of which are related to error term.
Okay. Sorry, just to cut you off, I'll be leaving now.
Yeah, okay, sure. Okay. Yeah.
Thank you. I'll just
Yeah.
watch the videos later.
Yeah, it will be uploaded by tomorrow so that by Monday you can be prepared. Okay.
Thank you. Thank you.
Yeah. Okay. So as with the simple linear regression, the 6 assumptions that we have are: number 1, a linear relationship exists between dependent and independent variable. A linear relationship exists between the dependent and independent variable. Dependent and independent variable. A linear relationship exists. Think. This was, don't you think that this was the premise on which with which we started with? Linear relationship obviously is going to exist. That is why the name is Introduction to Linear Regression and Multiple Regression. They say a linear relationship exists. Indirectly they are trying to say a non-linear ship ideally should not exist between a dependent and independent variable. Between a dependent and independent, that means between y and x, not between x1 and x2. Between y and x, y is equal to b0 plus b1 into x1 plus b2 into x2 plus e. So here dependent and independent is y and x1. That relationship should exist. The second assumption is that independent variables are random and no exact linear relationship exists between two independent variables. That means there should not be any linear relationship between x1 and x2. This is second assumption. So a linear relationship exists between y and x1. Perfect. That has to be. But x1 and x2 or any independent variable should not be linearly related. Non-linear relationship, again I am repeating, non-linear relationships are possible. So non-linear relationship, one second, non-linear relationships are possible.
The independent variables are not random, right?
Independent variables are not random. Sorry, are not random. Not random. That means randomness means that today we took some independent variable, tomorrow we are taking any other independent variable. Yes, it should not be random. It should be specified. It should be specified. The third is that expected value of the error term, that is E of the error term, should be equal to 0. E of the error term should be equal to 0. That means if you take, so if you recall our discussion in reading 1, I told you that what is error term? The error term is that my scatter plot is something like this. So there is no best fit line in the world which can pass through all the points. So what we do is we draw a best fit line and we assume that the points on this particular line are the estimated points. So these are the actual y's, these are the estimated y's, and the difference between the two are error term. And so it creates a multiple error terms, E1, E2, E3, etc. The concept over here is saying that if you take an average, if you try to calculate the mean of the error term, the mean value of error term, that means which will be calculated as E1 plus E2 plus En divided by n, it should be equal to 0. It should be equal to 0, which is logical because you are trying to draw what? You are trying to draw a best fit line. So suppose here the error term is positive, here the error term will be negative, here it is positive, here it has to be negative. So that negative positive in a way should cut out in such a manner that at the end the expected value of the error term should be equal to 0. The fourth assumption is that the variance of the error term should be constant for all observations. Variance of the error term should be constant for all observations. That means that whatever the variances you are trying to calculate from here, En square, E2 square, etc., even if the observed value of independent variables, that is x1 and x2, will change, the error terms may change, but when you will calculate the variance of set 1 and variance with set 2 independent variable, both the variances will have to be constant. The variances do not change for change in value of the independent variables. Are you getting the point? Are you getting the essence? over what we are trying to say, constant value for all observations. All observations means which observation? The observations of independent variables. So suppose I took a set of independent variable observations. Suppose cardinal health, S&P 500, that variable. Suppose I assume that S&P 500 return is 10% today. Okay, if that is 10%, then according to that I created a set of cardinal health values for different values of S&P 500, and I calculated the error term. The SD of the error term is, suppose SD of the error term is 10 or say 5. Okay, now when I take another set of independent variables, set of independent observation, that is, suppose I assume S&P 500 return to be suppose 20%. In that situation, the error terms will be different. The error terms, the values, individual values will be different. That is not the look point. The point at which we are looking at is that when you will calculate the SD from this new set of error terms, this SD will also be 5. This SD is not going to change. This is the core part that we are targeting at. And if this SD changes of the error term, that means there is a problem with the violation, which we will understand now only, basically heteroskedasticity, which we'll learn.
Are these assumptions for multiple regression, or are these assumptions for heteroskedasticity?
So this assumption is for multiple regression, and the violation of this assumption results in a problem which is called heteroskedasticity.
Okay.
Heteroskedasticity, multicollinearity, serial correlation are problems, are violations of the assumptions. I wish, as a statistical analyst, if you create a model, you will pray to God that you never face a situation of heteroskedasticity, multicollinearity, or serial correlation. Because if you do that, then you will have to tweak your model or make certain adjustments.
So these are assumptions, and if they're violated, then it's because of the heteroskedasticity.
These are the assumptions, and for each assumption there is a nomenclature. So if assumption 1 is violated, this kind of a problem arises. Assumption 2 is violated, this kind of a problem arises. Most predominant are the 3 assumptions. Okay, one is this one: variance of the error term has to be constant, expected value, all these results, and this particular thing, independent variable and no exact relationship. If this is violated, assumption 2, it results in a problem of autocorrelation, serial correlation. If this is violated, it results in a problem of multicollinearity or etc. If this is violated, this results in a problem of heteroskedasticity. So these are the 3 primary problems which a statistician may face. All the problems are not same. Understand? The problems also have different what you say, impact on the model. There are certain problems which may not impact the model severely, but these 3 problems may make your model unreliable. So if your model is unreliable, then how you will invest your money using that model? The fifth is, this fifth point is related to serial correlation. The error term for one observation is not correlated with the error term of another observation. The error term of one observation is not related with the error term of another observation. This is the fifth point. Okay, that means 2 error terms, E1 and E2, it should not be correlated with each other. It should not be correlated with each other. See what it is trying to say. It is trying to say One second. Here the error term of one observation indicates that E1 over here is not correlated with E1 over here. So one observation is 10%, the another observation is 20%. The set of E1 over here is not correlated with set of E2 over here. Because if that is correlated, again it kinds of create an impact, or it kinds of give a sense that it may so happen that as the value of the independent variable is increasing, then there can be a prediction possible. See, error term is said to be stochastic. Statistically it is said to be stochastic. Stochastic means random. Error term is something which can never be predicted. If you are able to predict your error term, understand what do you mean by error term. Here error term means the unexplained portion of the dependent variable. Error term means the unexplained portion in the dependent variable. So this is my ESS, explained sum of square. This is my uh, SSE, sum of square errors. So what I said was that suppose the movement in the dependent variable is 10, here it is 8, and here it is 2. That means out of the total movement in the dependent variable, or total variation in the dependent variable, 80% of the variation I can explain, 20% of the variation I cannot explain. This is what I said, correct? But when we say error term, it means that we cannot explain this 20% because this 20% is random in nature. It cannot be predicted. If there are signs of correlation, what is it trying to say? You know, I'm coming out of statistical uh, what you say verbose, and I'm trying to explain you in simple terms. If error term is what you say having correlation, or error term is not stochastic, that means that there is another variable, another any there is an independent variable which is not captured in this model, but which also have a predictive ability about the dependent variable. There is another variable x3 perhaps, which is also a good determinant of y, and you have not captured it over here in this model. So if you have not captured it in this model, automatically it lies where? In the error term. But this also have a high predictive ability about the y. So why have you kept it in E? You should take it out of E and put it over here in the model. You should take it out of E and put it over here in the model, if this is what it is trying to say or convey the message. That if your error terms are correlated, if there is if there is a relationship, there is a correlation that is there, that means that there is something which you have missed. You should find that, take that out and put it in your core model as an independent variable to make the error term completely stochastic. The last observation is that the error term is normally distributed. These 6 assumptions are highly testable in exam. Do remember that. This is very important concept that we have or we are discussing. You can, if you want, you can also note in your Spicer book, which is it this particular LOS to be very important, because this will lay premise for half of the content that is there, and this is highly testable in exam.
Are these definitions testable in the exam, or
Yes,
are they like indirectly intertwined into like these vignettes? Like,
they are directly testable also, they are indirectly testable also. In any way this can be tested. So they can give you a question in a vignette. They can give you a question where you will see that which of the following is not an assumption of multiple regression, or which of the following is correct or incorrect. So two of them will be incorrect, one will be correct, or vice versa, and those only will be related to the assumption, and they will twist the language. One example I showed over here. This is the real example question. What I told: independent variables are not random. Sorry, that's fine. And no exact, the linear word is omitted now. No exact relationship exists between two independent variable. Many students got confused that okay, there should not be any relationship between two independent variable, but that is wrong. The proposition only is that there should be no linear relationship. Non-linear relationships are possible. So this was incorrect for majority of the students. So these type
So
of
then,
questions, yeah.
Mohit, do you mind writing down like heteroskedasticity, like around like these six concepts? Do you mind writing down like the terms so that we can associate that better
Yeah, I
with?
will. That's why I've created the
Oh,
Excel.
okay.
I will share the
Oh,
Excel with
okay.
you.
Got it. Okay. Thank you.
Yeah.
Sorry.
Yeah.
just to clarify, Mohit, the non-linear relationships are possible, but that you're just saying that that's possible with the variables, not the independent and the dependent.
For dependent and independent also this is possible, but the primary reason why we do regression is based on the linear relationship. So the linear relationship has to be there between dependent and independent. When linear relationship exists, non-linear relationship can also exist. There is no comment in this entire reading 1 and reading 2, or in the entire regression, about non-linear relationship. That is out of our purview, because non-linear relationships are highly complex. So CFAI has not incorporated that in all these particular discussions or etc. But wherever I am saying linear, we or this particular text is saying linear, it absolutely means linear. It gives no comment about non-linear relationship. That you have to take. So here linear relationship exists, linear has to exist. Non-linear may exist, may or not exist, no comments. Here there should be no exact linear relationship between two independent. So no linear relationship, that we have to ensure. Non-linear can exist, cannot exist, no issues with that, or no comments on that. That is the thing.
Okay.
Okay, then let's start off with the next thing, which is LOSK, which is heteroskedasticity. Just one second. Okay, so first let me explain and then I will move into the Excel part. LOSK. Okay, what is it? Explain the types of heteroskedasticity and how heteroskedasticity and serial correlation affect statistical inference. This is the LOS statement. Now, what is heteroskedasticity? Here, in our assumption, we told in assumption 4 one second. We told in assumption 4 that variance of error terms should be constant across all observations. Okay. This particular assumption in itself, the name is homoskedasticity. Homoskedasticity means that the variance of the error terms is constant across all observation. That means we are abiding by the assumption. Violation of this assumption results in heteroskedasticity. That means what is heteroskedasticity? When variance of error term is not constant across all observation. Variance of error term is not constant across all observations. Okay, this results in heteroskedasticity. Now they say there can be two types of heteroskedastic situations possible. There can be two types of heteroskedastic situations possible. Number one is called unconditional heteroskedasticity. Unconditional heteroskedasticity. Okay, and number two is conditional heteroskedasticity. What is unconditional heteroskedasticity? It means that my error terms are not correlated. My error terms are not correlated. My variance of the error terms is not constant. I agree. However, this is purely randomly happening. This is purely randomly happening. That means this is not related to the level of independent variable. Or let me explain conditional first. Conditional heteroskedasticity says that my variance of the error term is related to the movement in the value or value of the independent variable. If the independent variable, taking an example, if an independent variable increases, my variance of the error term also increases. If the independent variable decreases, the value of the value of the condition value of the residual terms or variance of the residual terms also decreases. This is called conditional heteroskedasticity because there is a linkage of the value of independent variable and the value of the variance that we are getting from the error term. If this kind of linkage is there, this is a big issue in statistics. Automatically, if you got conditional heteroskedasticity, you will also be able to understand unconditional. Unconditional means heteroskedasticity is there, variance of the error term is not constant, agreed. However, there is no relationship of these movement or these variations or these different variation of error term with the value of independent variable. So there is no linkage. It may so happen that when value of independent variable is increasing, my error terms variance is decreasing at one time, also increasing at one time, also decreasing at one time. That means there is no predictive ability of the variance of error term and the value of independent variable movement. There is no predictive ability. In that situation, it is called unconditional heteroskedasticity. Okay. Statistically, we are not concerned more about unconditional heteroskedasticity compared to we are concerned more about the conditional heteroskedasticity. Okay. Let me explain diagrammatically also. Just one second. And yes, in exam, you can also expect diagram based questions. In exam, you can also expect diagram based questions. So I am putting both the types of things over here. Just one second. Suppose this is the best fit line. So this is my best fit line or regression line, whatever you want to say. Okay. And suppose this is the value of my independent variable. Value of independent variables. Okay. Over here we are measuring, and that's fine. And this is the variance of error term. If this be the statistical situation, in simple terms, we are trying to understand. See, if you see this particular graph, there is no major movement in the error term. There is no major movement in the error term. They are closely composite with each other. Closely composite with each other. That means they are very close to the this, and there is no material movement. Minor movements are there, that is human, like I'm drawing the diagram manually, so that's fine, but there is no major movement that is there. You cannot specifically identify that okay, this term is very low over here and this term is very high over here, or the terms at the lower value is low, the variation at the higher values are high. This we cannot specify or identify over here. When this kind of situation happens, this is called homoskedastic diagram. This is called homoskedastic situation. Okay. Now, what will the heteroskedastic situation look like? Again, we have a best fit line. We have a best fit line. Okay, that is the same. That is value of independent variable, and here it is variance of error terms. Okay, this will look something like this. Okay, and as you can observe yourself, in this particular area, where my value of independent variable is relatively low, my variance of the error term is also low. At least it is closely tied to the best fit line. It is closely tied to the best fit line. The value of the independent variable, sorry, the variance of the error term is also low. Okay, compared to when we are comparing it to this particular scenario, okay, this particular scenario, I hope you will be able to understand. Just 1 second. Okay, let me restrict this to this part over here. This and this scenario, both represents what? both represents that at high values of your independent variable, the variations is also high. So this is the diagram which will represent over here low residual variance, low residual variance, and this two diagram represents what? High residual, high residual variance at at high value of independent variables. Okay, this situation depicts what? This situation depicts the existence of heteroskedasticity. Okay, so in exam you are responsible to both diagrammatically understand also. That means they may present a diagram for this, and then they may ask you how you will deal with this particular thing, or a question related to heteroskedasticity. So you are responsible to know both.
Is it just basically to recognize the differences in the homoskedasticity and the heteroskedasticity?
Yeah, I mean, you have to understand that the variations in homoskedastic will be relatively equal. So you will look parallelity. It will not be variable. Variance will be like very low. And even if suppose they say in presenting this kind of a diagram, and they say that heteroskedasticity is there, you can safely mark this kind of a diagram as unconditional heteroskedasticity. Because as I said, heteroskedasticity can be conditional or unconditional. If it is unconditional skedasticity, in that situation, you it does not causes major statistical problems. So unconditional heteroskedasticity is not a major problem. But
So,
this, yeah, but this kind of a diagram will present existence of conditional heteroskedasticity. See, this can be reversed. I have given one scenario. We are taking one simple scenario that when independent variable value increases, the variance of the error term also increases. It may so happen that when independent variable value increases, the error term value decreases. And this diagram, the grouping may flip upside down. So this particular equation that you are seeing, the more variable portion, high residual, this may come on this side and this may come on the right side. That doesn't change my judgment about heteroskedasticity. This will always be a conditional heteroskedasticity.
would it ever say that on the left, the homoskedasticity, is this unconditional heteroskedasticity?
On the left, sorry, what do you said? Will they
So,
say?
yeah, so you're saying that unconditional heteroskedasticity doesn't really matter. It's
Doesn't matter. Doesn't
yeah.
matter. Yeah, it doesn't matter. So from exam point of view, if you are facing a situation of unconditional heteroskedasticity, you don't need to change anything. You will continue to work in the way you are working normally.
Okay, and then just for practical terms, the heteroskedasticity, is it because there's a lot of volatility in your independent variables? Is that why this happens?
It's not about yeah. So basically the concept at the assumption is variance of the error term should be constant, correct? And that variance is not constant for all independent values observed. So as the value of independent variable changes, my variance is changing. This is what is conditional what is heteroskedasticity. So okay, let me explain it practically. Think what the assumption is trying to say. share price of Cardinal Health is equal to 13 plus 0.75 S&P 500 return. Okay, our hypothetical example. Suppose what is the independent variable over here? S&P 500, correct?
Yeah.
That is my independent variable. Situation 1, I am taking various values to analyze my equation. Okay, in first value of S&P 500 is 10. If my value of S&P 500 is 10, then what do you think the value of the share price of Cardinal Health will be? Forecasted value of Cardinal Health will be
13 plus 7.5.
13 plus 10.5, which is I think 20.5, correct? This is the forecasted value. Okay, now you can take, in this scenario, you can take 9, 8, 7, anything, different values you can take. And here, okay, suppose you take 10 here and you observe a value, the actual value of Cardinal Health. The actual value of Cardinal Health is, let's assume 22. Now, what is the error term? Actual minus forecasted?
Yeah, 1 point. Is it
Minus 1.5. Minus 1.5. Suppose I take 9, the second day, another observation, another set of observation. I take 9 over here. Now 9 into 0.75. Can you help me with this forecasted value?
Is it just 19.5? Is that?
Yeah, 19.5. Thank you. Or 9 into 0.75. I don't think it will be 19.5. 9 into 0.75
right.
plus 13.
$19.75.
19.75. Okay. 19.75. Can you do plus 1.2, 1.5 over here? Plus 1.5.
Plus 19.75 plus 1.5 is 21.
21.25, I think,
Just
right? 21.25, right?
Oh, okay.
Okay, right? I'm explaining in simple terms. I'm not going in detail. Okay. This is my observation 1, or let's assume this is my observation 1, 9. This is my observation 2. Let's change the number 2 and 1 over here. Okay. When my independent variable is increasing, okay, what the assumption is saying, when my independent variable is increasing, my error term, suppose this is my variance of the error term. Suppose this is my variance of the error term. You can calculate the variance. It's not a big deal. The variance of the error term should be same. If this is same, that from 9 to 10 when I am going, my variance of the error term continues to be same, in that situation they say that this is homoskedastic, not an issue. This is what was expected. Suppose here it is 9 to 10 and here it happens is that this was minus 1.6 and this is minus 1.5. Suppose this is the situation. In that situation, what will happen is that this will increase. This is increasing because this is a negative sign. So lower number means the value is increasing. And suppose this is happening continuously for 8 and for 7. This was 1.7. This was minus 1.8. Okay. This is called heteroskedasticity. Different terms. Okay. Now, since here there is a rhythm that as my value is increasing, as my S&P 500 value observation set is increasing, the variance of the error term is also increasing. Okay, if this be the situation, these are negative terms, so lower number means increasing. This is also increasing. This is called conditional heteroskedasticity, and this is a problem. There is another set, suppose, which is first till here. Is it clear what I'm trying to convey? What is the problem and what was the correct? If all values would have been minus 1.5, homoskedasticity perfect. If all values for my different independent variable S&P 500 values is in a continuous trend, is following a continuous trend. Okay, so when it is increasing, it is also increasing. It can happen vice versa also. When it is increasing, all these are decreasing. It can also happen vice versa, not an issue. But point is they are following a trend. If that kind of a relation exists, then it is called what? Then it is called conditional heteroskedasticity. Then it is called conditional heteroskedasticity. Big problem. It is a big problem because all my statistical inferences are gone. My model is not reliable. If the statistical inferences are not reliable, automatically my estimates will not be reliable. So everything is gone basically. You cannot invest money. You cannot make money from the model in simple terms. Okay. The
What,
yeah.
what is that? What is that column next to the error? In between your share price and
Actual value.
like
Actual value of actual value of share price of Cardinal Health. See, this is the predicted value, correct? And this is the observed value. What we told, how we calculate error term: actual price, actual value minus predicted value. This is how you calculate the error term, right?
yes.
So this is what is actual value and this is predicted value. This is error term. This is a big problem. Till here, any question?
No.
Right?
No question.
No question, right? Now the third situation, which is midway problem, but not a big problem, that is unconditional heteroskedasticity, is here the value is minus 1.4, here it is minus 1.7, here it is minus 1.6, here it is minus 1.5. So there is no relationship between the variance is not constant, so problem, but there is no relationship of this movement with the movement in the value of independent variable. At this is increasing, but this is at time increasing, at time decreasing, at time increasing, at time decreasing. So there is no rhythm, there is no tone in the movement, there is no relationship between the movement in independent variable and the variance in error term. This is the situation of unconditional heteroskedasticity problem, but not a major problem. Okay, I try to lay down in real terms. I try to lay down because this simple example is a it gives you a peek into the real terms of what we are trying to understand. Here it may so have happened that this statistical nomenclature and the way of diagrammatic presentation would have overswayed what in real terms we are trying to look at. This is reality of life. When you will prepare your model and when you will try to apply it, this is what you will look at, the reality. I forecasted the share price of Cardinal Health to be 20.5 according to my model. The actual value on that day was 22. Okay, there is an error in my model. The error term is minus 1.5. Now repeatedly when you keep on tracking it again and again, it will give you a series of data. You can plot it in Excel, and then that error term series will help you find the variance of the error term and so on and so forth. Then it will continue. Okay, so this is how reality will look like or reality will work. Is this clear what I was trying to communicate?
Yes.
Okay. Okay, so this is clear, right? Heteroskedasticity, the concept that we have discussed now.
Yes.
Yes.
Okay. Okay, so let's just 1 second. Yeah. Now the effect of heteroskedasticity. Okay. So if this is clear, let's move into that effect part. I think directly over there. Okay. Just 1 second. Next is effect of heteroskedasticity. Okay. There are 4 effects of heteroskedasticity. Number 1, which I have already told you, that coefficient of independent variables will not be impacted by this heteroskedasticity. Coefficient of independent variables will not be impacted by this heteroskedasticity. Okay, so the standard errors will be unreliable because I told that if error term is wrong, SEE will be wrong, and if SEE will be wrong, then all the standard errors of the coefficient will also be wrong. Okay, so the standard error of the coefficients are unreliable. Okay, standard error of the coefficients are unreliable. The coefficients are not impacted. So the coefficients are not impacted. That means they are same. They are correct. Okay. So what is impacted is the standard error. Number 3 is, so I have already explained, if standard error is too small or too large, then what will happen? So that is something which we know. And t test and f test will be unreliable. So these are the effects of heteroskedasticity. Basically, one part of the test, that is standard error, is getting impacted, because of which all our test becomes unreliable. If you are not able to test the model, automatically you will not be able to execute the model, okay, or rely on the model. Okay, this was the second aspect. The third aspect is detecting heteroskedasticity. How do we detect heteroskedasticity? So they say there are two ways you can detect a heteroskedasticity. Number one is by drawing a scatter plot. So just like we did over here with a limited data, like this one, what you can do is, for a series of Excel, you can plot, just like we created over here in tabular format, the outcomes, and the error values, the standard error values. What you can do is, the value of X and the variance of the error term you can calculate, and then you can select these two rows in Excel and you can create a scatter plot. Just by looking at the scatter plot, you will be able to understand, or you will be able to get a sense of whether heteroskedasticity exists or it does not exist. So if you get anywhere this kind of a sense that this is happening, then automatically you will be able to understand the existence of heteroskedasticity. Otherwise it is not. Okay, so if we take an example which is there in our textbook as well, they have presented the equation, or they have presented the diagram in this particular way. Just one second. Suppose this is my independent variable. The value of independent variable is increasing. Okay, so this is my independent variable. Okay, and these are the values. In the lower values it is fine, but as the values increases, the volatility and the range for this data also increases. So see the vividness over here, the gap was only this much, but as we move over here, the gap has increased to this much. This clearly indicates the existence of heteroskedasticity. Just by creating a scatter plot and by looking at the scatter plot only, if you are experienced enough or if you have an idea, you will be able to detect heteroskedasticity. It will be as easy as that. Okay. The second way to detect a heteroskedasticity, which is a more mathematical way, is Bruce-Pagan chi-square test. Bruce-Pagan, it is also called BP. So Bruce-Pagan or BP chi test. Okay, it will be a chi one-tail test. I will explain why it is a one-tail, why it is not a two-tail. But this is another way of detecting heteroskedasticity. Okay, now understand it very carefully because this is bit more intellectual. Okay, although it is not presented in that way, but there are some hidden explanations which on rereading I was like and referring from other books I was able to understand. So just understand the logic of this. It is very intelligent concept, I would say. What they are doing in Bruce-Pagan chi-square test is, suppose this was your normal ordinary regression equation or first regression equation. Y is equal to b0 plus b1 into x1 plus b2 into x2 plus e. Or let's take a more simpler value. Let's take only one independent variable, that is ei. Okay. Now here we have observed already that when you plot this equation, share price and S&P 500, then there was only one independent variable, and you can create a series of data. On one set of series is the different observed values of S&P 500, which is my independent variable, and on the other side you have different values for error terms, correct? Now what you have to do is, what this model says is, create a second order regression equation or create a new regression equation. Okay, create a new regression equation. So this is my first or ordinary or original regression equation where y is the dependent variable and x is the independent variable, and error term is something which we know. Okay, now this model says create a new regression equation, and in this equation what are you going to do? In this equation we are going to regress squared residuals on the independent variables, so my error term square, all my error terms, these values becomes my dependent variable in the new equation. Think, broaden the aspect of, or broaden the perspective of thinking. I am doing a new regression over here where error terms, I am regressing error terms against the values of independent variable. I am regressing the error terms against the value of independent variable. So my error terms becomes y in the second equation or in the new equation, and this becomes x. So y will be replaced by the squared error terms. Y will be replaced by, in the new equation, not replaced, in the new equation my dependent variable will be e square is equal to b0 plus b1 into x1 plus e, another e is different over here. So let's not confuse it, let's create in this manner. So this is a new regression equation where you are regressing the error terms against the independent variable. You are regressing the error terms against the independent variable. Think, what are you trying to do, or what Bruce-Pagan is trying to do? It is trying to understand that how much of the variation in the error term. Normally, what do you understand over here? By creating a r square, and calculate the r square over here. We will calculate the r square over here. What is r square? Coefficient of determination. What does r square help us understand? ESS by TSS, that is explained sum of square by total sum of square. That is how much of the total variation in the dependent variable is being explained by the movement in the independent variable. Okay, does it have any explanatory power? Because if it has any explanatory power, that means that the movement is being explained by the movement in the independent variable. That means error term and independent variable are related to each other. That means variance of the error term and the independent variable are related to each other, and hence heteroskedasticity exists. This is a mathematical way of doing things. The scatter plot was more of a judgmental way. You cannot conclude the degree of heteroskedasticity that exists. But here you are mathematically proving it, and you are able to understand the degree of heteroskedasticity as well. Okay. Again, I'm explaining you. This is only putting thing in the right perspective. No new knowledge I have explained till now. First, we are creating a regression equation where we are regressing the squared error term. Squared error term means variance of error term against the independent variable. Possible? It is possible. Just like you created this equation where you had the dependent variables data, the independent variables data, and you regressed both against each other so that you are able to create this equation in very similar manner. I am doing that same ordinary regression equation where I am regressing the squared error terms against the observed value of independent variables. Once I do that, I will get a regression equation. Correct? This is a normal. Now stop thinking as a new equation. Think of it as a normal equation. Okay. Think of this error term as a y. Okay. Now, how do you calculate? What is the measure? What we are trying to understand? We are trying to understand that if there is any change in value of x, whether the movement in or the variation in the value of independent variable, does it have any explanatory power regarding the movement or variation in the error term? This is what we are trying to conclude, right? And here, by looking at the r square value, we can calculate that, because r square gives us the explanatory power of my model. R square gives the explanatory power of my model. So if in this particular equation r square has a value, that means that portion of the variation in the error term, in the squared error term, is being explained by the movement in the independent variable. Now you can use that r square to test the level of heteroskedasticity or degree of explanatory power it has. As a statistician or as a model developer, you will always want this r square to be 0, because you don't want to show that your independent variable has an explanatory power with regards to the standard with regards to the variance of error terms, because this proves the existence of heteroskedasticity. Is the logic clear? I will explain the test, and test is very easy. So numerically you can test, but is the logic clear?
So I just want to repeat back what I heard. So if to create a new regression equation, we should square the terms.
Square the error terms.
Excuse me, square the error terms.
Because 1 second, because what is variance? Squaring the error terms, squaring the normal terms also. If suppose I ask you to calculate variance of anything, what is that variance? E summation x minus x mean square, correct? That is what we call it variance. So squaring the error term is not a new logic, because in my equation or in my heteroskedasticity, from day one, from the start only, we were dealing with variance. That is why that squaring concept has come in.
Okay.
Like what I wanted to say is that when we are saying square of error, it should not be perceived as a new knowledge, because heteroskedasticity is dealing with variance of error term, not the error term itself. It is not dealing with the mean of the error term. It is dealing with variance of the error term. And how do we calculate variance? We all know that variance is always square. That is why, if you recall, we used to write percentage square, and then we told that percentage square is meaningless and let's use standard deviation. So that is why we introduced standard deviation in our life. In level 1, if you recall, this knowledge was clearly discussed. So here we are dealing with variance, and variance is always a square term of anything.
Okay, thank you. Yeah, yeah, that makes sense.
Yeah, you can continue. I stopped you in between. So yes, squared of error terms.
Oh, okay. Then as far as the flip, I think I got lost a little bit
Yeah,
there.
right.
So the x becomes y and the y becomes x. And that also, so we square the error term and then we flip the variables.
Yeah, 1 second, just one correction over here. Y is no longer here in this equation. Here error terms becomes y and x remains x.
Okay.
So the dependent variable is no longer there continued in this equation. My target is to see, my target is what? My target is to understand whether independent variation in independent variable and the variation in the error term, are they related or are they unrelated? This is what I am trying to understand, correct? So here what I am trying to do is I am trying to take a square of error term which is there, which is created from here, and I regress it against the original independent variable. Okay, if this model has any predictive ability, or if this model has a R square, then it means that the both are related. That means variation in independent variable is able to explain the variation in the error term. And if this happens, that means there is a predictive ability and there is a existence of heteroskedasticity. If this model or this is not able to explain any variation in error term, automatically R square will be 0. And if R square is 0, that means that independent variable and error term are not related, or that is not being able to explain any variation in the error term.
So for a problem like this, when they ask you to find the Bruce Pagan test,
Right.
are they going to put it in the form of R squared equals RSS over TSS, or are they going to give you E squared equals intercept plus B1 times X?
See, this is something which I explained you for the purpose of knowledge, so that you get the essence. Now, as I am saying that now when we will do the mathematical test, then it will be very easy for you to perform that in exam. So exam will not be an issue, because here there is a standard way of testing. If you get this question, there will be a standard way in which you will test and you will proceed ahead. What I wanted to explain over here you was the gist or the core of the matter, that why is it flowing in that particular order, what is the logic behind that, which I found somewhere or the other missing in the textbook. So that is why I went into a bit you can say bit more detailed analogy. Okay, now let me do one thing. And yes, on the second question, yes, you can be given R square, ESS and TSS, because R square is something which you are expected to know. So you can be asked to calculate R square value, or you can be directly given R square, but you will most probably not be supplied with this equation, this error term, this second equation you will not be supplied with. Okay, now let's do the test. It will be very easy. So it's not a difficult test at all. It is very easy. Just 1 second. BP chi-square test. So the test statistic you will get is BP chi-square test. BP chi-square test. That is the test statistic calculation is n into R square residual. That is the second equation, R square of the residual equation. Okay, not the first equation. So if suppose they give you 2R square, if suppose original equation R square is something, second equation, the regression equations R square of error term is this, we were supposed to take the R square of the residual terms or the error terms, not the original equations R square. Do remember that, because we are not testing the first equation, we are testing the equation of variance of error terms against the independent variable. Okay, so this will give you your chi-square test automatically. This will be the chi value that you will get, and you can use the chi table to get the chi critical value. Now you can automatically compare, and do remember that this will always be a one tail test. Do remember that this will always be a one tail test. This will always be a one tail test. Because why it will be a one tail test? Because see, what I am concerned over here is that model having explanatory power. That means this r square value in terms is practically in terms is greater than 0. If it is not, if it is less than 0 or near 0, then I'm not concerned with that, because less than 0 or near 0 is something which is expected. That means it is not heteroskedastic. My concern on my test point over here is to prove the heteroskedasticity. So that is why it will be only a one tail test looking for a higher value of r square, or looking for a higher value of a chi test. If the value is high, that means it is a, if the value is high, that means it is a heteroskedasticity is present. If the value is low, I am not concerned because heteroskedasticity is not present. Okay, let's solve an example. check.
Okay, so I feel like this one is pretty straightforward. So if the n is 60 and r squared of the residual is 0.08, so that will
0.08 means 8%. So here we will have to take R in percentage. Just one thing. Otherwise, always the value will be low. Take R in R square in percentage, not in decimal.
okay. Oh, so it'd be 8% is what
Right.
you're saying.
Right. Yes, it's 8%.
Okay, so then it would be 60 times, so it'd be 480? I don't feel
60
like
times 8.
to me that's 480, but it just seems so.
So I'm sorry. I made a mistake. I reversed this thing. R square should be in decimal, not in percentage. Sorry. Should be in decimal, not in percentage. In
So then it would be 4.8?
yeah.
Okay.
So the BP chi test value would be 4.8. BP chi statistic value or chi stat value will be n into r square, and we are supposed to take this r square of the squared error terms regressed against independent variable, which is 60 into 0.08, which will give you 4.8 value. Now you can look at chi critical value. What is the chi critical value? Again, look at the chi table. 5 square, 5%, chi 5% table. So I think it's appendix C. Chi 5% table, the probability in the right tail 0.05, and supposedly at 60, so 0.05 and the degrees of freedom is 1, because okay, I have not mentioned over here. Take the degree of freedom as 1. Take the degree of freedom as 1. So below 5% in front of 1, below 5% and in front of 1, the value that you get is
3.841.
3.841. So 3.841 and 4.8. Now automatically, since this particular thing, like if you draw the table over here, if you draw the chi table, and if you try to draw that particular curve, this is the 5% value, 3.841. Our concern is always greater, not lesser. So this region would have been failed to reject null. Failed to reject null. And this region is reject null. Okay. And here the value lies, which is 4.8. So we reject null and conclude that heteroskedasticity is present. We reject null and conclude that heteroskedasticity is present. Any which ways, in simple terms, if you want to understand, if the BP chi stat value will be greater than the chi critical value, because this is a one tail test, If BP chi-stat value is greater than chi-critical value, it will always conclude that heteroskedasticity is present. Is present. If you want, you can write this also in your Schweizer notebook somewhere. This will make things easier for you to remember. This is always true. This is always true. And so to be specific, you can say that conditional heteroskedasticity is present. Conditional heteroskedasticity is present.
This test is specifically testing if heteroskedasticity is present or not.
Yeah, this
Okay.
test proves mathematically. So the statistical plot, or sorry, scatter plot is more of a subjective thing. You may have a different view, I may have a different view. As well as the problem with scatter plot is it does not inform me about the degree, or it does not give me a sense about the degree of heteroskedasticity, while the BP test is giving me numerical, first numerically testing, so there is no subjectivity involved, everyone will conclude same, and second, it gives me a sense of the numerical extent as well. Suppose if the r square value instead of 8% would increase to 12% or 15%, that will make things more worse in terms of heteroskedasticity. And if it reduces, then obviously it will be less impactful.
So if we fail to reject the null, then it isn't present.
Yeah, the null hypothesis is that it is not present. So if we fail to reject null, we conclude that the problem of conditional heteroskedasticity is there. Our alternate was heteroskedasticity is there. Null was heteroskedasticity is not there. So we have rejected null. That means we conclude that heteroskedasticity is there.
Okay, that's really okay. So we in this problem we reject the null. So we are saying that heteroskedasticity
Heteroskedasticity, yeah, it is there,
is present.
is
Okay.
present.
So if we fail to reject the null, then it is not present.
It is not present. You will fail to reject null when the BP chi-stat will be less than the chi-critical.
Okay. And why is the degree of freedom 1?
Because there is only one observation. There is one dependent variable over here. If suppose there would be two dependent, I'm saying two independent variable, then it will be 2. And automatically you can think of it in one more way. Normally in your cases it will be 1, because generally error terms are regressed against one independent variable individually. Generally, I'm not saying there is not a static or uniform rule, but generally when an error term test is done, the heteroskedasticity test is done, it can be done with multiple independent variables together, or it can be done individually one by one. So suppose error term x1, error term x2, error term x3. So that is why this equation will always have one independent variable, and that is why the degree of freedom is 1.
Okay, so the degree of freedom is k. It's not n minus
No,
k.
it is k.
Okay.
Yes, it is k. In chi test, it is k. Any other question? No. Last concept is uh, correcting heteroskedasticity. Last concept is correcting. Okay, one second. Text, using text is more easier. Correcting heteroskedasticity. Okay, so this is very simple. Again, there are two ways to correct heteroskedasticity. The number one way is use of robust standard errors. See, the problem that once you detect that heteroskedasticity is there, the only problem that you will face is with regards to the standard errors, correct? That the standard error of the coefficient is incorrect. So if the standard errors are not incorrect, then automatically the t stat and the f stat will also be incorrect. To correct for this particular standard errors, the first way is to calculate the robust standard errors. So two ways to solve for the problem are: number one, use of robust standard errors. Okay, use of robust standard errors. These are also called white corrected standard errors. These are also called, so also known as white corrected standard errors. Okay, so in this situation what will happen is that you don't need to calculate, because calculation is not in there in your syllabus. You will be supplied with the values of robust standard errors in exam. If the vignette hints or suggests existence of heteroskedasticity, then in that situation you will have to use robust standard errors. You will not be using normal standard error, while both the things will be given to you in the vignette, but you will have to use robust standard errors. If the what you say, the heteroskedasticity is not there, then they will not supply you with robust standard errors. So most probably uh, kind of robust standard errors will give you a hint of existence of heteroskedasticity. Okay, and the value of the method of calculation of t test remains unchanged. So it's just that when you are calculating t stat, instead of using normal standard error you will use robust standard error, that's it. And the f test also doesn't change, so both will remain as is. You will have to use only this error, and this calculation is not there in your curriculum, so you will be supplied with the robust standard error value. Okay, the second way to solve this particular thing is yeah, to modify the original equation, to modify the original equation. Okay, so what you do is you look back at the original equation, the original data, then you tweak that original equation to adjust for heteroskedasticity. Okay, so this second part is obviously not there as part of our curriculum. In terms of that, it is only there mentioned as a reference that this is also solution, but otherwise nothing to do with that, or it cannot be tested in any way in exam. This is something which can be tested in only one particular way, where the values will be given to you.
Okay, so what you're saying is just understand that when they ask for this, they're just going to give you the value and you just plug it in.
Yeah, that's it.
Okay.
That's it. Okay, one second. Let's solve an example with robust standard, although that's particularly same, that's not an issue at all, but still let's solve this example as well. So Example 3. An analyst, the equation is so this is the question. It's a straightforward one, not complicated one. So
Okay, so it's just the 0.6 divide 0.31
right,
equals
and
1.94.
right, and what does it lead to? We is it we reject null or we fail to reject null?
We fail to reject null because it's at 1.98.
We fail to reject null, and what do we conclude then?
Um,
Is
it
it
is statistically not significant.
Not significant. Correct. So when solution, when heteroskedasticity is present, then okay, T stat is equal to how much? 0.60 divided by 0.31, which is equal to 1.94. Since this is in range of minus 1.98 to plus 1.98, we conclude that this is we fail to reject null and conclude that inflation is not statistically significant. That inflation is not statistically significant. Okay. How would your analogy change, or does it make sense to use robust standard errors? Because what would have happened if we would not have used robust standard errors? If
Your
we,
t-test would be higher.
okay, so if we would not have used the white corrected standard error, our our t stat equals to 0.60 divide 0.28. What is the value?
2.14?
2.14, which is greater than 1.98, leading to rejecting the null hypothesis. And incorrectly concluding that inflation is statistically significant. Okay, so it does matter, or its use is helpful. Okay, is it fine?
Yeah.
Yeah.
Are they going to ask us if this is like a type 1 or type 2?
They can. That's a good question. I was expecting that. They can ask. That would be bit more kind of a top 10% questions, you can say, because that would be linking the R1 and the R2 and in bit of a complicated order. So that kind of a test could be, you can think of it in that way, that independent correlation, suppose standard errors are increasing. If you recall, we discussed just now what will happen if standard errors are too high. Then we said that the t-stat value would be too low. It will result in rejecting the null hypothesis when it is true, which is a type 2 error, which is a type 1 error, if you recall. So
Type 1.
Type 1. So that linkage is possible. Cross linkage is possible.
Okay. And then for this one, it's the degrees of freedom is basically n minus 1 minus 1, because k is 1.
Yeah,
so n
this is
minus
normal. T n minus
Okay.
k minus 1.
Okay.
So if it would have been 2 or 3, like independent variable, it would have been n minus k minus 1. Okay.
So just to clarify, the last statement that you made, if we had used the 2.4 and it's greater than 1.98, we would have rejected the null, and that's a type 1 error.
That's a type 1 error. Yeah. We would have incorrectly concluded that inflation is statistically significant. That means we would have continued to include inflation in our model, but ideally we should remove inflation out of our model because inflation is not statistically significant. So that means inflation is not able to explain the movement in the or the variation in the T-bill rates. Any other question? Any other doubts?
No, not for me.
Okay. Okay, then in that case, we are done for the session for today.